so this is part 2 of that lesson. This is a summary of those formulas we just spent some time developing. So here is your arithmetic sequence. This is called an explicit formula. Just another vocabulary word. We're going to learn something called recursion too. So this one is just your basic function formula. So these are the 2 we did. And then if I wrote them with function notation with f of n versus a sub n, basically this would just be a different type of notation. Instead of calling this a sub 1, we would call it f of 1. Okay. I will tell you this is kind of a Common Core thing. No one ever uses function notation other than in Common Core for sequences, but we are showing it just because it's kind of left over. I know we don't have our regions this year, but we're going to mostly do the subscripts, but also use this a little bit. But realize it's no different. So here in this table, I'm not going to do all of them, okay? I'm going to do a couple just so we kind of get the idea. I'm probably going to do about 4. That should be good. So I'm going to do the top 4. So first off, we're going to put it in a table, which is not something we do a whole lot. But the point is that you get that it can be represented in a table as a function. So we would call this n and a sub n instead of x and y. So I have 4 terms here. They're 6, 9, 12, and 15. Okay. Deciding if it's arithmetic or geometric, we look and we see we have an adding pattern. So it's arithmetic. I'm just going to write an A here for that. And basically, also at the same time, we want to identify what the value of the common difference is, and we're adding 3. So writing our formula, I'm going to scroll up this time just to kind of talk about where I got it from. Okay, so I'm thinking y equals mx plus b, right? Except we're using that notation. So my slope or difference is 3. We're shifting it over 1, so instead of just putting x, we're using the letter n. And we're shifting it over 1, okay, to the right. And then my a sub 1 goes last. So that's my a sub 1 is 6. So I do plus 6. Now I could simplify this, so I could multiply it out. Okay, I'm not going to do that this time. I might do one later just to kind of show you what I mean, but that's fine. That's kind of what we're looking for when we talk about the formula. Okay, so looking at this one, same deal. I'm probably going to be a little scrunched here with a fraction. I'm going to write it sideways, which I don't love to do, but there's your 4 terms. So looking at this one, I don't see an adding pattern because then I would be minus 6 minus 3. Like it doesn't add or subtract the same thing. To look for, maybe it's not obvious that it's a multiplying pattern, I can divide the 2 terms. So I take the second one and divide it by the first. So 6 divided by 12 is 0.5 or 1/2. 3 divided by 6. So the third divided by the second term, we're just seeing how we're multiplying, is 1/2. This one would work the same. So if I look times 1/2 times 1/2 times 1/2 times 1/2, that does work. So this is geometric, and my common ratio is 1/2. So writing my formula, I have a start value of, let's see, we start with 12. Let me just change colors, it's getting kind of messy here. So this is a times b to the x, but we're doing a sub 1 times b shifted over to the n minus 1. Okay, so that's my sequence formula. That one is a whole lot harder to simplify. It is like 99% of the time left like that. There is ways to make it like shifted over and stuff, but we're not going to worry about it. Okay, so sometimes we have formulas where we have to work backwards. So we have the formula and we're going to generate the terms so that we can see the sequence. Now, I don't ever really recommend trying to look at the formula and figure it out when you're just starting out. So what we're actually going to do here is find a sub 1, find a sub 2, a sub 3, and so on. Okay, so I'm just going to find the first 3. I could find more if I had more space, but we're just going to do that. You're supposed to find 4, but we'll do 3. So here, to find a sub 1, that just means I'm plugging in a 1. So I do negative 1.5 times 1 minus 1, or 0, plus 24. So this is just, 0 plus 24 is 24. okay? I have negative 1.5 now times 2 minus 1. We're just plugging in values. So this is negative 1.5 plus 24 is 22.5. Okay. And then negative 1.5 times 3 minus 1 plus 24. Okay, so that's going to be negative 3 plus 24 is 21. Okay, so this sequence of numbers right now is 24, 22.5, 21. I can see the pattern of subtracting 1.5, which is also kind of seen in this formula by this d value, because this is written in the normal form we're used to. So here the next number would be 19.5. So here's my list of numbers. Since this is just kind of like an instructional video, I could erase all this. I could write my table here, right? As I said, I think this is enough. I think with these two table examples, we get what's going on. Because we're adding a negative number each time, so that counts as arithmetic. And my d value, the number I'm subtracting, right, or the number I'm adding, but it ends up, we think of it like subtracting because it's getting smaller, is negative 1.5. Okay. The point here is I really go back and plug in the numbers to find that pattern. There are other ways to write sequence formulas where you won't recognize what the D and the start value are. So even though this does match up, like this is the 24, and that's my first term, that's the difference, that's what I'm subtracting, they can get tricky with some of the questions. Okay, so last one from a table. I will always start and just go to my sequence of numbers. Okay. Now here I see a multiplying pattern. If I take any term and divide it by the one in front of it, here I get my common ratio as negative 3. So it's geometric. The ratio is negative 3. Not really something, so this flip-flop negative positive thing is not really something we do with regular functions that are continuous because it would mess things up if I tried to plug in the numbers in between, okay? But it is something we do with sequences. So this is a sub n equals, and actually, you know what? This one has function notation in the table, so I'm just going to use this one to kind of show you what the function notation would look like. So instead of a sub n, I do f of n, okay? My start value, or my a sub 1, is 6 times negative 3 to the n minus 1. So it's really not different. You're just putting an f of n in the front, okay? This is called f of 1, but once I plug something in, it's just, the same difference as a sub 1. So for the video, we are going to skip forward. There's a couple other examples here. I'm going to do just letter H. Yeah, letter H is good. Okay, and then I'll do a couple down here. So f of n here, notice it's more in an mx plus b form than an a sub 1 times n minus 1 plus d form. I'm sorry, d times n minus 1 plus a sub 1 form. So here, it's really important that I actually plug in those numbers to find out what's going on. Okay, so if I plug in a 1, I get 6 times 1 minus 4. So that's 6 minus 4 is 2. This is 6 times 2 minus 4. So that is 12 minus 4 is 8. And then this one is 6 times 3 minus 4. So this is 18 minus 4 is 14. And I'll just figure out the last one on my own. So I can see that adding 6 pattern. So this is going to be 20 for my last one. Now notice this is not the a sub 1 value, and that's because this is written in a different form. If we think backwards, f of 0 would be negative 4, but we don't want that in a sequence. We want to start out with the first term f of 1, okay? So that's why plugging them in, because you can write your formulas different ways, is the best way to make sure you get the right terms. So in a table, right, right? This is my table. I'm just putting those numbers in the table. This is arithmetic, and the common difference is 6. So the last type of question you'll get with these is you'll have a sequence and you'll be asked to find a term that's way down the sequence, and that would take forever. And yeah, you could just list numbers out for a really long time, but that's not the most efficient way to do things. So I'm actually going to do letter A and letter C for this one. So we want to find the 25th term in the sequence. When I look at my sequence, things I notice, first off, important information, I'm starting with a -7. My common difference, it looks like we have a difference here, and we're adding 3. Now I could just continue to add 3 and write 5 and 8, right, and 11, but the point is, what happens if they asked for the 1,000th term, okay? I don't want to waste my time doing that forever. So if I write a formula for it, I can just plug in the number of the term. So the formula for this, it's d times n minus 1 plus a sub 1. So we have 3 is d, that's like our slope, shifted over, n minus 1, and then my a sub 1 is a -7. So now if I say I want to find the 25th term, I'm asking for a sub 25. So that means if I'm finding a sub 25, I'm just plugging a 25 in for the end. It's just an evaluation, and I can get the answer from there. So if I type that in my calculator, which is really all I have to do from there, a sub 25 equals 65. Okay, so let's look at letter C. We only have to get to a sub 8, so this is another one. We would call it brute force if we just listed out the terms that, yeah, we could do it, but we want to kind of be a little more efficient. So here, maybe I notice the common ratio, maybe I don't. It's not an adding pattern, I can see that. So if I do 3.5 divided by 0.5, that gives me 7, which we can kind of see because we know what 35 divided by 5 is. And then just to check, 24.5 divided by 3.5 is also 7. So we're pretty sure we have that constant multiplying pattern by 7. So I'm starting out with 0.5, my common ratio, 7. So my function, and I'm actually just going to write it without actually writing the function out. I'm going to actually plug in the 8, okay? So let's just write a sub 8. My start value, my a sub 1 is 0.5. My common ratio is 7. To the n minus 1, because we're plugging in an 8, is 8 minus 1. And if I type that in my calculator, I would get 411,771.5. And we know geometric sequences are really exponential functions, so that kind of crazy growth does not necessarily surprise me.